recording for group 2. We did the thermocouple experiment last week. So just a little overview of the presentation. First, I'll be giving the background, just kind of the procedure in the experiment, some of the theory involved in this experiment, the data that was collected, and other considerations that would slightly vary the experiment. So during this experiment, we used a type K thermocouple to measure the change of temperature when either placed into boiling water or ice water. Some of the equipment used was the type K thermocouple, boiling water and ice water, and then a computer with a PDAQ data acquisition system. So this is kind of just a repeat. Sorry about the little typo right there, but the experiment procedure involved bringing the boiling water, ice water to constant temperature, inserting the thermocouple and collecting the reading up until a constant temperature, and then removing the thermocouple and allowing the thermocouple to reach a constant close to the temperatures at room temperature. So the main instrument used was the type A thermocouple. The approximate range is about -400 degrees to over 2,000 degrees Fahrenheit. And this particular thermocouple had a 1/8 inch diameter. So some of the theory involved using the lump capacitance method. This is where the temperature of the solid that we're considering is uniform throughout. And in this case, it was a thermocouple that was involved. So from this first equation right here, we can see that the energy balance of the system when integrated involves coming to the normalized room temperature, and then e to the negative t over 1 over the time constant. So more on the time constant theory is that whenever we have high density, high specific heat, or high volume, those all lead to increased time constants. So when we have a larger time constant, that means it's longer for the heat transfer to occur. And vice versa, when the lower the time constant is, the faster you'll have heating of a solid. So the expected results we can have from this equation is that when the initial temperature is low, we're going to have heating and reaching an average value after a few time constants, and vice versa for cooling of the thermocouple. So during this boiling water procedure, you can see initially there's a small spike. That was because we kind of had a little accumulator, got the thermocouple too close to the boiling water, which is going to lead to increased little spike. But then after that, when we inserted it, you can see a sharp rise in the temperature immediately, and then it begins to flatten off as it reaches a steady temperature. And then we eventually removed the thermocouple and allowed it to cool to close to room temperature. And here's the insertion data. So around, you can see it doesn't take very long for the thermocouple to reach roughly point of boiling temperature of water. So then we normalize the data, which is the temperature at a specific time minus the ambient temperature of the boiling water over the initial temperature minus the ambient temperature. You can see that this is the plot of this, which can be used to then figure out our natural log of our normalized temperature versus time. And finally, this is inversing those, switching those axes allow us to see the time versus the natural log of the normalized temperature. And I was having a little bit of an issue on Excel, but the time constant I received there was roughly 0.4, which is pretty low, so you're going to have a steep, you're going to have a very fast temperature heat transfer, which will allow the temperature to increase very fast. So during the removal of the boiling water, you can see that's a lot more steady. And then skipping ahead to the time versus the natural log of the cooling temperature, you can see that even though this equation is wrong again, I was having problems with Excel, but I had a time constant of roughly 82, which is going to mean your rate of heat transfer is slower than having boiling water, and this is because the temperature difference of the ambient is there's not as much of a temperature gradient in the atmosphere as there would be in boiling water. So this is the ice water experiment. I'm going to kind of skip over this just because Chase and Liz will be talking more about that. So just some other considerations that we would have in this experiment is that if you were moving the thermocouple around, that would increase your convection coefficient, which would lead to a change in your temperature. So if I was moving the thermocouple during the cooling process, it would cool faster since it has a higher convection coefficient. So just to wrap up some conclusions, the lump capacitance method was used to assume a constant temperature within variance within the thermocouple, and we were allowed to see during this experiment the rates of heating and cooling, as well as how the time constant can affect how fast you heat up or cool down. And thank you. Any questions?